This question is about predicting the stronger ionic compound. This picture here on the left is meant to represent the ordered arrangement of just two dimensions of an ionic compound, anion and cation. Energy is added to this, let's just say in the form of heat, to separate the ions entirely from one another. There are two main factors to consider when predicting how much energy it would take to separate ions completely from one another. And the first one is the magnitude of the charge of the cation and the anion. What that means is that if you have a +1 cation and a -1 anion compared with a +2 and a -1, it's going to take more energy to separate these because the magnitude of the charge, the magnitude of the cation is larger. Okay, so the magnitude of the charge is the first thing to consider right there. Now let's say it's a tie. The second thing you consider is the atomic radius or the atomic volume or the atomic size. And the reason for that is that the distance that the charges are from each other matter. Consider just your refrigerator on the magnet on a refrigerator. It sticks to the refrigerator when it's very close. But if you take that magnet only a little bit farther away, the distance from the charge depreciates with an inverse to the square, and then it just, the magnet doesn't stick anymore. In this example here, the magnitude of the charge, I'm going to erase this example so it doesn't muddy up our thought process. We are comparing these two ionic compounds here for which one would take the most energy to separate the ions 100% from each other. The magnitude of the charge is a wash. So when we look at the atomic size, the larger atoms, it's a further distance apart these nuclei are from each other. So it's going to take less energy to separate these guys from each other. Let's do a couple examples and pairings here that are from the homework. The ionic compound KF versus CSF. Potassium fluoride versus cesium fluoride. Okay. When we look at our charges to determine the magnitude of the charge, we find the columns that the cations and anions are in. We notice that it's a metal and a non-metal, metal and a non-metal. They're both ionic compounds. The cations are both +1 in nature, and the anions are identical, -1 in nature right here. So we're not looking at a difference of magnitude of charge. That's a wash. So now we go and determine the atomic size. We find potassium and cesium on our periodic table and note the trend of atomic size. Let's draw a couple kind of pictures to kind of show that a bit. I've tried to draw the fluoride anions identical in size because they are identical right there. And the cation, I've tried to draw the larger atom with a larger volume diameter of space right here. Which one is going to take more energy to separate the ions completely from each other? It is going to be the potassium fluoride because it has the smaller atomic size. Let's look at another pairing. Oops, I wanted MgO versus MgF2. Let's look, we first start with the magnitude of the charge. We find these are both ionic compounds, metal, nonmetal, metal, nonmetal. Magnesium is +2. I'm just going to draw, because it's identical, +2 right there. Let's look at our anions. Oxygen is a -2, and we have 2 fluorines right here. Okay. We first look at the magnitude of the charge. The anions are of different charge, and the MgO has a higher magnitude. It is negative dose. So we don't even consider atomic size in this example. We can go as far as to say, look, this -2 is going to be more attracted to the +2, so to take more energy to separate those ions from each other. I hope this helps. Thank you.